So far, we've looked at modeling systems in one dimension, and in this video, I'm going to model a two-dimensional system. So what we have here are two masses, and they're connected by a string. And this is a pulley right here, so this is free to spin, this pulley, and we have a frictionless surface. So right here, you can pretend the surface has ice or some other slick surface. So this is frictionless. So if this surface is frictionless, as soon as you let this block M1 go, block M2 is going to start accelerating downwards. And since they're connected by a string, it's going to pull block M1 along with it. And due to the nature of this system and many systems, sometimes they're coupled with some sort of connecting object. And in this case, we have this rope that's connecting these two blocks. So if M2 starts accelerating downward, well, then M1 is going to start accelerating with the same magnitude. It's just going to be pointing in a different direction. So the acceleration of block 2 is going to be downward, but the length of the vector will be the same for A1, and it'll be pointing, obviously, to the right. It's going to start accelerating to the right as block M2 starts accelerating downwards. So these two accelerations have the same magnitude. So the magnitude of A1 is going to be equal to the magnitude of A2. Their directions will be different, but the actual magnitudes of these two accelerations are the same. And with a system like this, we pretty much treat them the same as a system with one dimension. The strategy is the same. So you look at each individual object, and then you create a free body diagram for each object. So let's do that. So for the first object, M1, I'm going to, as always, represent it with just a dot. And let's look first at the vertical forces. So we have an upward force from this surface, this floor, onto the block. So that would be a normal force. So we'll have that pointing upward. And this is a normal force that's pointing upward. And obviously it's not accelerating in the vertical direction, it's just sitting here on this surface. So the weight force is going to be equal and opposite to the normal force. So these two will be the same magnitude. And the weight force, again, we can represent it with a W, and I'll call it W1 since this is mass 1. And this is going to be equal to then the mass of block 1 times gravity. So this comes from Newton's second law. The force equals the mass times the acceleration, and the acceleration in this case is the acceleration due to gravity. And that's it. That's the vertical components of the free body diagram for M1. There's nothing else that's acting on it in the vertical direction. So we see, once this box is let go, that there's going to be, again, this tension force that's pulling to the right, that's causing it to accelerate. And the tension force comes from the string. So we'll have some tension force that's pulling off to the right, like so. And that's what's causing it to accelerate to the right. There's going to be nothing that's pointing to the left because we said that this is a frictionless surface. So this is actually the complete free body diagram for object M1 for this mass. So this is the complete free body diagram. And now we can look at the second object, M2. And what are the forces that are acting on M2? So we know that we have another weight force, and I'm going to represent M2 here with another dot. So we have another weight force that is pulling downward. And it's not necessarily, we don't know if these are equal masses, so it could be greater than or less than the weight force of mass 1. We're not really sure. But the weight force, and we'll call this W2, is going to be equal to m2 times gravity. And that's the weight force. And we're going to have, again, an upward tension force. But we know that this block is accelerating downwards, so the weight force has to be longer than the tension force. And I want to be careful here because I want to try to get the length of this vector to be equal to the length of this rightward vector, because this is the same string. So this is the same tension force in mass m1 and in mass m2. They're pointing different directions, but the magnitudes need to be the same. So I'm going to just adjust these vectors. I want to be sure that the tension force is the same length for both free body diagrams. And that looks pretty close. And I'm also going to, just to make it more obvious, I'm going to lengthen this W2 vector, because we need to be very clear in showing that this vector is longer than the tension force. If this vector was not as long as the tension force, or if they were equal length, then this system wouldn't accelerate. If the tension force was equal to the weight force, then the mass m2 would just stay here and we would have no acceleration. So by showing that W2 is longer than the tension force, we know that there is more force in the downward direction, therefore the acceleration will be downward. So that is my second free body diagram. So we see both objects have an acceleration, a1 and a2, they're equal length. And we have these two free body diagrams now that are showing us the forces in each direction for both objects. So like we did with the one-dimensional case, we're first going to start with the general equations. So we have the general equations, and we are starting from Newton's second law. So we know that we're going to have two different directions for this first object. So if I'm looking at this first object, I'll divide this, and we'll do object M1 on the left, and we'll do object M2 on the right. So we're going to have these different objects, and I'm going to start with the x direction. So Newton's second law says that the sum of the forces in the x direction equals the mass times acceleration. Okay, and so now I'm looking now at the horizontal forces, and we see it is only the tension force. So only the tension force is working in the horizontal direction. And of course, we're treating standard directions with x being horizontal and y being vertical. So, all right, so what are my forces in the x direction? Well, there's only one, and that is tension. So tension is the sum of the forces. There's only one. And what is the mass we're dealing with? We're dealing with mass 1. And we are dealing with the same acceleration. So magnitude of A1 equals the magnitude of A2. So instead of specifying A1 or A2, these are the same magnitudes. I'm just going to call this A, because I'm going to use this same acceleration A in both the first object's case and then also in the equation for the second object. So this is now a specific equation for the x direction. So this is a specific equation that is unique to this problem. So I'll give that just a red box here. So this is a specific equation. The tension equals m1 times the acceleration. Okay, so now I'm going to do the forces in the y direction. So I'm looking at this and I see that I have N, the normal force, pointing upwards, and the weight force pointing downwards. And, well, what is the value going to be of the sum of these two forces? If I add this upward vector to this downward vector, what is the sum of those going to be? So if I add this upward vector to this downward vector, the sum of these two vectors is going to be 0. because it's not accelerating in the vertical direction. So instead of writing Newton's second law of F equals ma, what I'm instead going to write is the sum of the forces in the y direction are equal to 0. And you could get that from writing Newton's second law in a prior step. If you wanted to do that first, you could. You just have to know, well, the acceleration is 0. So if the acceleration is 0, then this right-hand side is 0. So that's why I just skipped this step. We look at these vectors and we see, well, if I add normal force to the weight force, I have 0 force. There's 0 force in the vertical direction because we're only accelerating in the horizontal direction for block 1. So if the sum of the forces in the y direction equals 0, well, now I can write that. So I have a positive normal force, and I have a negative weight force that I'm going to write as m1g. And that's equal to 0. And then I can add m1g to both sides, like so. And what do we see from this equation then? We have the normal force is equal to m1g. So now we have this other general equation that describes the vertical motion, the behavior in the vertical direction of block m1. We see it's not accelerating, so we know, of course, then that the normal force equals m1 times gravity. So now I'm looking at this second object, and I'm going to label this as another specific equation. So we have 2 equations for the first object. Now I'm going to look at the second object, and I see immediately that I don't have anything in the horizontal direction. So we're not going to have any sort of equation for the horizontal direction. There's no forces that are working horizontally. So I'm just going to start with the sum of the forces in the y direction are equal to the mass times acceleration. And now I look, okay, what are the 2 forces now I have? I have a positive tension force minus m2g, because m2g, the weight force, is pointing downwards, and this is equal to, well, my mass is m2, and what is my acceleration in this case? And it might be tempting to say g, but the actual acceleration of this block, remember we stated, was a2. And a2 is equal to a1, and we've just started calling that a because it's shared between both blocks. Both blocks are going to be moving with some acceleration a. I can even write that explicitly up here. I can say we're now going to call this a. So this same acceleration is going to exist for both blocks. So this is going to be mass 2 times a, the shared acceleration of both blocks. And then I can solve this now for tension. So if I add m2g to both sides, now I can solve this other equation for tension. And the reason I want to do that is because I have already an equation that's equal to tension on the left-hand side for the first object. This object here is equal to tension. And now I've figured out this other object that has also a component of tension. And when we look at the equation of motion, we see that these tensions are shared. So if I were to move forward with this problem, or there was some problem that gave me some values or something like that, I could put these 2 equations equal to each other. I could say that m1a is equal to m2a plus m2g because they're both equal to t. So if this one is equal to t and this one is equal to t, well, then they're equal to each other. So that's how these 2 equations are coupled. So we found 3 specific equations for these 2 objects that have motion in 2 dimensions. the first object had forces acting in 2 dimensions. The second object had forces only acting in the vertical direction. But we saw then that both these objects are coupled. They have this shared force T from the rope that's between them. The tension is the same all throughout this rope. So wherever you would look in this rope, it's going to have the same amount of tension. So that's how we found this coupled equation over here, where we can combine the specific equations for both objects, and then that can help us solve problems.